Well, students, right here again. Today we got notes for section 4.2 out of the book. Read the section, watch the video here, and take anything that we need to help you for the quiz. 4.2, we talk defining the atom. We have 3 objectives here. Make sure you're done with this section, done with the chapter. You know what these are. You need to be able to define the atom. You need to distinguish between the different subatomic particles. And you need to be able to describe the structure of the atom. Review vocab. Got model and visual, verbal, and mathematical explanation of data collected from many experiments. Here's our new terms we'll be coming along to. And then our main idea, an atom is made of a nucleus containing protons and neutrons. Electrons move around the nucleus. That gives the basic description of an atom. Here's our definition of an atom. Smallest particle of an element that retains the properties of the element is called an atom. Have a thing called a scanning tunneling microscope, STM. This is what we can see the atoms with. It gives a nice representation of the atoms. On page 107 in your textbook, figure 5 shows a picture from a scanning tunneling microscope. When electric charge is applied, a ray of radiation travels from cathode to anode. Is called a cathode ray. Cathode rays are streams of particles carrying a negative charge, and these particles with negative charge are known as electrons. And here is a cathode ray tube. This would be figure 6 from page 107. Gets a little more information on it. There's a cathode ray tube. Got your cathode, you got your anode connected up to a voltage source, a battery. And you have a glass tube that has been connected to vacuum pump, so it's a vacuum. And then we get this little electron beam passing through it. J.J. Thomson did some work with the cathode ray tube, and he was able to determine the charge to mass ratio of a charged particle compared to known values, and figured out it was much less than a hydrogen atom, the smallest known atom. And doing this, he figured out the first subatomic particle, the electron. And how he did this illustrated at the top of page 108. In figure 7, he took this cathode ray tube, brought positive and negative things up next to it, and then noted the thing bent towards a positive. The beam bent towards the positive plate. So it was attracted to it. So he knew it was a negatively charged particle. Early 1910s, a guy named Millikan used what we call the oil draft apparatus to determine the charge of an electron. It's illustrated here. This would be Figure 8 on page 109 in your textbook. We're going to find a little more information on this. Charges change in discrete amounts. This turns out to be 1.602 times 10 to the negative 19th coulombs, which is the charge of one electron. Now, we just call it a negative 1. We don't use this value here. But using all of this, Millikan calculated the mass of a single electron, which was this number here. It turns out to be 1 over 1,840 the mass of a hydrogen atom, which a mass of a hydrogen atom is essentially due just to a proton. So it takes roughly 1,800 electrons to equal the mass of one proton. Matter is neutral. You know this because you don't get shocked when you touch things under normal conditions. But if electrons are negative and are in matter, how is matter neutral? So Thomson proposed a model to answer this question, and we called this Thomson's plum pudding model. It said the atom, he just took what Dalton had described roughly a century earlier and modified it a little. Dalton was considering the atom to be just a solid sphere. So Dalton just thought it was a solid sphere. So that was Dalton. With the discovery of the electrons, Thomson modified it. He kept it kind of a solid sphere, but he said it was a positively charged sphere. And then there's electrons distributed in here, like little bits of plum in the plum pudding. I've seen it described as a chocolate chip ice cream model, something that's more common today. A plum pudding was very common in Thomson's day in England. Then we move along a little farther, and a guy named Rutherford looked at how positively charged alpha particles interact with solid matter. And he aimed particles at a thin sheet of gold foil. He expected the paths of the alpha particles to be only slightly altered. So what he expected was that they're just going to fly right on through, maybe just be bent around a little bit. Here he was considering this plum pudding model, but he was surprised. This is not what happened. This is his illustration of his model, and he had alpha particles being shot out through the piece of gold foil. Some did kind of go right on through. Some bent a little bit. But said most of the particles went through the gold foil. A few of them bounced back, some at large angles. So some came here, made long angles, some almost came straight back. So they went many different directions, not what he expected. So with this, he concluded the atoms were mostly empty space, and almost all of the atom's positive charge and almost all of its mass contained a dense region called the nucleus. So Rutherford figured out there was a nucleus in the atom. So keep those two together. and electrons are held within their atom by their attraction to the positively charged nucleus. Got that positive negative attraction on. There we go. Here we have what he looked at happening. So as these electrons were coming through, if they weren't very close to the nucleus, they just passed right on through. If it came close to that nucleus, then they went off all kinds of different directions. As they come close to that positive, the alpha particles were positively charged. Two positives repel each other. So boom, boom, all kinds of different directions. And then Rutherford refined the model later to have things called protons in there. So Rutherford also protons. So Rutherford protons and the nucleus. And then move along a few more years, and James Chadwick in 1935 figured out there are neutrons in the nucleus. This was due to figuring out the masses weren't matching up. So we now have the three main subatomic particles, like 1935. So once we found that first one, it didn't take too long to find the next two. And then we get to what our basic model is today. All atoms is made of three fundamental subatomic particles: proton, neutron, and electrons. Atoms are spherical shaped. They're mostly empty space. Electrons travel around the nucleus, held in attraction to the positively charged electrons. And then we got table 4.3 here, which gives the basic information we need. Now you're going to need to know the names, the symbols, the location, the charge, relative mass. You don't need to know the actual mass, but get it written down in your notes. But you don't have to know that one. But know these other ones. So. And then something we won't get into much in this course, but just a brief thing that we do have. Know that protons and neutrons are composed of subatomic particles called quarks. So these do not affect chemical properties, so we don't consider them in this course. In a physics course, we'd get more into the quarks. So scientists do not yet understand how or if quarks affect chemical behavior. Right now, this appears they do not. So chemical behavior can be considered by looking only at an atom's electrons, which we're going to in chapter 5 is all about electrons and atoms. So when we get to chapter 5, we look a lot at electrons. Atoms are mostly empty space. They're not solid spheres. That's what Dalton thought. But over time we figured out, no. And they're not mostly positive or negative. In a way, these are actually equal, so not most of all it's negative. But empty space. And where are the two fundamental subatomic particles? What are the two subatomic particles found in nucleus? In nucleus, we find protons and neutrons. Do not find an electron in the nucleus. It's in the outside part. It's in what we call the electron cloud. So I meant A and C weren't right. And the positron's not a term we're using here. So that's a little bit on 4.2. Again, should have already read the section, added any other things you found in there that didn't talk about here as I went through this PowerPoint. But know this stuff, be ready for a quiz in a couple weeks probably. So that's it for now.